Welcome to my channel. Today's chapter is going to be on shear force and bending moment. Chapter and bending moment. Okay. This is question number 1. Question number 2.1 came in the year 1991. 1991. Okay. This is GATE 1991. Okay. Now, while I'll be reading the question, I'll be pointing out certain notable points. So you need to hear me carefully. Okay. A beam having a double cantilever attached at the midspan as shown in the figure. The nature of the force in the beam AB. Now, this is the simply supported beam. Okay. At the middle point, this is the middle point. Point C is the middle point. Okay. The beam is loaded like this, as given in the figure. The angle is 90 degree. This angle is 90 degree. So this is the load P. Load P is acting like this. Now lengths are given like CD and CF is equal. This is CD and CF is equal. DE and FG is equal. DE means this one and FG is equal. AC and CB is equal. That is from here. That is the midpoint of the simply supported beam. Okay. AC, CB. Now, question number 2.1 came in the year GATE. (1991). Okay. Let me draw the diagram here. This is P. This point is also P. Okay. This is the simply supported beam. A, B, C. This is F. This is G. This is D. This point is E. Okay. Now in this case, what we are going to do is that we need to transfer the forces. Okay. That is from P. This is the P. This is also P force. We are going to transfer the force P from E and G to D and F. That is, this force will be going in here and this force will be going in here. Let me draw a fresh diagram. This is P. This is P. Okay. Now since the load is being transferred from here to here, from E to D, there will be a moment, okay? So we are going to copy the effect of the moment. We are going to take the effect of the moment. So this is the moment. Here the moment will be acting in anti-clockwise direction, like this. P, L. Let this length be L. Okay. I'm considering this length to be L. That is ED is equal to FG is equal to L. Okay. Let us consider this. So this is PL. Similarly, at this point, the moment will be in clockwise direction. This is in clockwise direction. This is PL. Okay. This is clockwise and this is anti-clockwise. Now what we are going to do is that we are going to do the same mechanism, that is we are going to transfer this force P and this force P at the middle point C. This point is C, this point is say F, this point is what was that, D, this is A, this is B. Okay. Now what we are going to do is we are again going to transfer these forces at the point C. Therefore, if we do this, the diagram will be like this. At the middle point, that is say this point, the load is 2P. Now there are two moments acting. One in the clockwise direction, okay, this is PL, another anti-clockwise direction, this is also PL. Okay, this point is C, this point is A, this point is B. Now therefore this clockwise and anti-clockwise direction moment will cancel out each other. Okay, so therefore what we are left with is the load P. A, B, at this point this is the load, this is 2P at C. Okay, therefore I can say that the beam will carry only bending moment and shear force. The beam will only okay. So our option is option A, bending moment and shear force. For question number 2.2, came in the year GATE 1994. Okay, the question is, the cantilever beam carved in plane is subjected to a lateral load will develop at any section, what is the nature of the force will be developed in this beam. Okay, now here says the cantilever beam curved in plane. Curved in plane means if this is a cantilever beam is supposed to be straight, okay, but in this case the cantilever beam is curved like this. Curved cantilever beam. Okay, this is a curved cantilever beam. It is asking what will be the nature of forces will be acting, and the loading is lateral load. Loading is lateral, that is load are acting like this. These are lateral loads. Since the number of load is not mentioned, I am going to take 4. Okay, so if I write like this, a curved cantilever beam, loads are placed like this. Okay, therefore I can say that number 1, this is 2.2. Okay, number 1, due to lateral load the beam will generate shear force and bending moment. Okay, that is due to lateral the beam will generate bending moment and shear force. Okay, however there is a second point, that is due to the curved nature torsional moment. Okay, this is the lateral load. And this is the curve. Okay, so one is due to lateral load and the other is due to curved nature. It will produce bending moment, shear force and torsional moment. Okay, so our option is in this case is bending moment, shear force and torsional moment. That is option number D. Bending moment, twisting moment and shear force. Here twisting moment is the torsional moment. Okay, this is the torsional moment. Twisting moment and torsional moment are same. Question number 2.3 came in the year 1995. Okay. If the shear force at a section of a beam under bending is equal to 0, then the bending moment at the section is. It is saying the relation between shear force and bending moment. We need to find the relation between shear force and bending moment. Now, what will be? Say, suppose this is very important. This is very important. Say, S is the shear force. Okay. W is the load intensity. M is the bending moment. Okay. Okay. Now, about the relationship. The relationship is given as d square m by dx is equal to ddx of s is equal to plus minus w. This relation is very important. What I'm trying to say is that double derivative of bending moment equal derivative of shear force is equal to plus minus w. Here, plus sign indicate the loading is in the upward direction. Say, this is the beam and the loading is in the upward direction of the beam. Okay, this is the load intensity. So in this case, positive loading intensity, there is plus w, and this is the same beam and the loading is in downward direction. It means negative loading minus w. Okay. Now, what is given in the question is that the shear force S is equal to 0. Therefore, we can write from this equation that d square m by dx square is equal to ds dx, integrating both sides we get that dm dx, that is slope of bending moment, will give us shear force, right? This is called slope of bending moment. is equal to shear force. And according to the question, this shear force is 0. Therefore, on further integrating, we can say that the moment is equal to constant. So, in this case, this is the answer. And option is, I think it's most probably D. Option D, constant. The bending moment is constant. Okay. Now for the next question. Now this particular question came in the year 1995. Okay. This is gate. (1995). The magnitude of a beam, magnitude of the bending moment at fixed support of the beam is equal to, this is the fixed support, this region is the fixed support. Now this is a propped cantilever with a load P at its free end. Okay. Now there are mainly two methods to solve this question. Okay. So let us add a page. Question number 2.4. Method 1. Method 1. This is A, this is B. Okay. This is point B. This is point A. This is the fixed point. Okay. This is RB, the reaction force at B, and this is P. Okay. Now what we are going to do is we are going to take the moment that is for the span BC, say this point is C. Now for the span BC, we are going to consider the moment which is acting at this point. We are going to consider the moment PA will be acting at the point B. Okay. So we can write it like this. This is RB, this is option B. The moment is in clockwise direction. This is PA. PA is the moment. Okay. This is point B, A. Now we are going to apply the superposition theorem of deflection. So I'm going to write like this, applying superposition theorem to find deflection at B. Okay. So suppose superposition theorem allows us to individually take the moment or individually take the forces acting on a point and add them up simultaneously. That is what I'm trying to say is that, say for the first part, we are going to just draw the beam, okay, and apply the moment, say PA. P is the moment and only the moment. Okay. Now we are going to assume that the beam has been deflected. This is the deflected shape of the beam. The deflection is termed as delta 1. Okay. And equation of delta 1 is given as, there is a proper equation for every deflection. Okay. This is acting like a cantilever beam with a moment at its free end. Therefore, the deflection for this will be PA whole square, which is the moment, into B, which is the length of the beam, by 2AE or EI, 2EI. Okay. This is one deflection. Now for the second case, we are going to consider the same moment, same beam. I'm writing like here, the same beam. Now what we are doing, we are taking the action of forces only. This is the force RB. The beam is getting deflected like this. This is the deflected shape of the beam. This is given as delta 2. Now, delta 2 is given as RB into BQ, which is the length of the cantilever beam, by 3EI. Now what we are going to do is that we are going to write that deflection at point B, delta B, is equal to delta 1 plus delta 2. Now since it is a propped cantilever, at this point there will be no deflection, so the deflection will be 0. Okay, this is very important. Now this is the superposition theorem. We are going to add up the deflection. Okay. Now for the solution, we can write that delta B is equal to delta 1 plus delta 2 is equal to 0, right? Therefore, we are going to write like here, it is in the downward direction, it is in the upward direction. We are considering downward deflection to be negative. This is negative and this is positive. Okay. So we are going to write like this, that minus PA into B square by 2EI plus RB B cube by 3EI is equal to 0. I have written something wrong here. This will be PB square. Okay, PB square, M B square by 2EI. Therefore, after solving, we get that RB will be equal to 3 by 2 PA by B. Now for the next step, we are going to consider moment about A, that is from the fixed support. This is point A, this is B. Okay, this is A, this is B. So Here what we are going to do is that we are going to consider summation of moment about MA, taking moment about MA. Therefore, I can write like this. Now, taking summation of moment about MA is equal to RB into B minus PA. This is the diagram we are following. Okay. RB, which is acting here in the upward direction, like in the anti-clockwise direction, and PA in the clockwise direction. Okay. So we are writing like this: 3 by 2 PA by B into B minus PA. B is cancelling out each other, and this is PA by 2. Okay. This is the answer. Now this is method 1. Now for the method 2. Question number 2.4. Method 2. Method 2 is based on carryover factor. Now bear with me, I'm going to write a formula and I'm going to explain them. Okay. So this is the formula. We are going to write carryover factor this is COF is equal to carryover moment at far end by applied moment at the near end. Now what is far end, what is near end? Say let me draw a beam. This is fixed. This is a roller support. Okay. Now what we are saying is that we are going to apply a moment in this here. This is the near end. And this is the far end. Similarly, this is near end. This is far end. This is fixed. And this is hinged. Okay. So based on far end, the applied moment of near end will change. That is, say we are going to apply a moment here like this. This is a moment M. Moment M. According to carryover factor, the carryover factor is stated that the carryover factor will be half when far end is fixed. Okay, and it will be equal to 0 when far end hinged. This is important. Far end fixed, far end hinged. So the moment, that is the transferred moment, will be, here in this case, will act in the same direction, that is in the clockwise direction, like this, and the moment will be m by 2, as m is the moment, that is carryover moment at far end by carryover moment at near end. Therefore carryover moment at far end will be equal to carryover factor multiplied by applied moment at near end. That is what I am trying to say, is that carryover moment at far end will be equal to carryover factor into near end moment. Therefore the moment here will be m by 2, as the far end is fixed, so it will be half, near end is m, so it is m by 2. Similarly for this case it will be 0. There will be no moment in this case. You can draw like this with a moment sign, m is equal to 0. Okay. Now this is the concept. Now to apply this concept on our question. This is the fixed support. Okay. The moment applied here is like this. This is PA. This is the near end moment, that is MB. Okay. This point is B. This point is A. Okay. The moment at point B is PA. This is the reaction force, RB acting at like this. It is irrelevant. So the moment at the far end will be like this. This is the moment, MA is equal to MB by 2, which is equal to PA by 2. This is near end, this is far end. Okay. So for the formula we can write that carryover factor is equal to MA by MB, which is equal to half. Since the far end is fixed, so it is half. Therefore MA will be equal to half into MB, which is PA by 2. This is the answer. Method 2. Question number 2.4 is very important. Okay. This is very, very important. The concept is very important. Okay. Question number 2.5 came in the year GATE 1997. Okay. This is based on deflection. Deflection of beam. But no problem, I'm going to explain it like here. A prop cantilever of span L is loaded with uniformly distributed load of intensity W per unit length all throughout the span. The bending moment at the fixed end is. We need to find the bending moment at the fixed end. Now, in this case, we are going to apply the same method as we have applied in this case. That is, we are going to apply method 1. Okay? Same application method of superposition and so on. So first, let us draw the beam. Now, it is a prop cantilever beam. So, this is the cantilever beam and this is the prop end. Okay. This is the load intensity. It is W per unit length. Okay. This end is B. This is A. Okay. Now what we are going to do, we are going to apply the method of superposition. Applying method of superposition. Okay. That is, we are taking the same beam and applying the load one after another, and then we are going to add it up, their deflection. So this is the prop cantilever beam with only the UDL is converted into a cantilever beam with UDL only. Okay. The deflected shape of the beam will be like this. This is the deflected shape. This is delta 1. Okay. Now suppose this span is L. Okay. Forgot to consider this span. This is span L. This point is B. This is A. So delta 1 is given as load intensity W, length to the power 4 by 8 EI. Okay. Since it is downward direction, it is negative. Now, we are going to consider the same beam and apply the prop end. Reaction due to the prop end. This is RB. Okay. This point is B. This point is A. Length is L. Okay. Now in this case, the deflected shape of the beam is like this in the upward direction. So I can say that this is delta 2. Okay. So delta 2 is given as R L cube by 3 EI. This is positive as it is in the upward direction. Okay. Now what we are doing is that we are going to write deflection at point B is equal to deflection due to UDL plus deflection due to point load, which is equal to 0. So here we can write that minus of WL to the power 4 by 8 EI plus R L cube by 3 EI is equal to 0. After solving, we get that R is equal to 3 by 8 W into L. Okay. Now let us draw the beam. This is the beam. This is the reaction R. Okay. This is the UDL, W per unit length. Now in this section, we are going to consider a section right here as XX. That is, we are going to find the bending moment at this section XX. Okay. The distance is given as X. The reaction is 3 by 8 W into L. This is W per unit length. Okay. So I'm going to write Mx, that is bending moment at section X, is equal to, this is in the anti-clockwise direction and this is in clockwise direction. Say I'm going to consider here for this now minus R into X plus W, which is the UDL, into X is the distance, into X by 2. What we did is that we converted the uniformly distributed load into a point load. Okay, W into X, and we are consider the centroidal distance from here, which is X by 2. At X is equal to L, that is, when the entire length of the beam is considered, this section XS will align with fixed end A. So I can write that at X equal to L, moment at A will be minus RL plus W into L square by 2. So we are just going to solve it. Minus 3 by 8 W into L square plus WL square by 8, not 8 but 2. Is equal to W L square by 8. This is our answer. Okay. Most probably it's option number A. Option number A. W L square by 8. Okay. Now this type of question is very important. usually come in the ESE also. It comes in the ESE, Engineering Service Exam, and it's very important. Okay, that's it for today. Thank you for watching, and we'll continue in the next video. Don't forget to subscribe and like my video. Thank you.